and in today's lecture we will start the last chapter of this course, that is sediment transport. So before we start this chapter, what is sediment transport, why this topic is important. So I will continue with the problem that we started using the Buckingham's pi method. Clear? So the problem statement was that for find an expression for the drag force on smooth sphere of diameter d moving with a uniform velocity v in a fluid density rho and dynamic viscosity mu. So now these parameters are given to us, and we have to use the dimensional analysis to develop a functional relationship between the variables. Now, the Buckingham's method, the procedure that we follow, that is the step-by-step method. Clear? Or it is called method of repeating variables. Now, in this case, you see that the first step in the method is that we have to list the parameters. So now remember that these parameters are given in these questions. So let's say you are a researcher, you are working in a new fluid mechanics phenomena or problem, you are exploring that. So that will be your job to identify the parameters, that what are the dependent, what are the independent variables. So this will not be given. So you can see the first step is the difficult step, because you can see here that if you miss important parameter or you bring some additional unnecessary parameter, so you can see there will be no advantage of this. Why? Because if you miss important parameter, the results will be incomplete. If you bring additional parameters to try to solve the problem, then the effort to do the work, that will increase, but of no benefit. So that's why you see that this step number one, actually this is the important step. So anyhow, because we are learning how to apply the methods of dimensional analysis, so that's why in the problems these parameters are given to us. So the step number one in the Buckingham's pi method says that you list the parameters, the dependent, the independent variables, and you calculate n. So n is equal to 5. It means the total number of parameters that are significant for this specific fluid mechanics problem, these are 5 total, dependent, independent, combined. Step number two is that we have to select either the MLT system or the FLT system, mass length time or the force length time the system, because we have the method dimensional analysis. So we have to use the dimensions of these parameters. So as we discussed in the previous lecture, so these two are related to each other by the Newton's second law. So you use the MLT system or you use the FLT system, you must get the same result. The reason here is that, and you can check as a learning exercise, that in some problems, if we use the MLT system, it becomes easy. While for some cases, if you use the FLT system, it becomes easy to solve. Other than this, if you use the MLT system or the FLT system, you must get the same answer. So this is not a question that should I solve it using MLT system or FLT system. The only reason is with some problem, if you work with MLT system, the solution becomes easy. It is possible. For some cases, maybe you work with FLT system and the solution becomes easy. But if you use both, they should work for you and you should get the same result. And the reason is that these are interconvertible. So in step number two, what we do is that we define the dimensions of these parameters. So if you make any mistake here, definitely the results will be inaccurate. So that's why you see that at every step we need to be very careful. Now step number 2 says that you calculate M. M is the number of fundamental dimensions present. This M is the number of fundamental dimensions present. So you can see here that M is present, L is present, T is present. So M is equal to 3. If, for example, M was present, L was present, and there was no T, then in that case M will be 2. So M is the number of fundamental dimensions present. Now step number 3 is that we calculate the reduction factor K, the reduction number K. Actually, in the Buckingham-Pi theorem, it says that these are the number of parameters involved in the specific problem, and these are the number of fundamental dimensions present. So the Buckingham-Pi theorem says that we can reduce these variables or parameters into how many dimensionless groups, which we call the pi groups. So as I said in the previous class that we answer 2 questions. The question number 1 is that for any problem, the parameters which we identify, how we can reduce them into how many dimensionless groups or products, which we call the pi terms. So this is the first question. So for example, in this question, 5 parameters are given. So the question is that we can reduce these 5 parameters into how many dimensionless groups or products or pi terms. So this question is answered by the Buckingham-Pi theorem. And the theorem says that if there are n number of parameters and m number of fundamental dimensions present, so n minus m, that will give us the number of pi's. This is what we defined the Buckingham-Pi theorem, number of pi's. Pi means the dimensionless group. Because Buckingham denote their dimensionless group by pi, so that's why commonly we use this notation pi, the uppercase. Clear? In some books also the lowercase is used, that we commonly use this lowercase. But anyhow, in our textbook, the uppercase, so we use like this. So now in this case, this n minus m, so it means that 5 minus 3, it means that 2 pi's are needed to solve the problem, 2 pi's. It means that these 5 parameters we can reduce to 2 parameters, 2 dimensionless products or 2 dimensionless groups, whatever you call, and these we call as the pi terms. So this is the first question that we try to answer. The second question that we try to answer is that what are these groups? For example, you will have pi 1 and we will have pi 2. So what are these? This is the second question that we have to answer. So these 2 questions we have to answer. The first thing is how many pi groups are required to solve this problem. That is answered by the Buckingham-Pi theorem. And then what are those groups? 2, 3, 4, depend on the nature of the question. What are these groups? So these are the 2 questions that we try to answer. Clear? Now the question here is that this n minus m, this is according to the Buckingham-Pi theorem, we get 2 pi groups. However, in your textbook, we go for step number 3, and instead of n minus m, we have to go for n minus k. Clear? As I said before that this m, most of the time it will be equal to k. The theorem says that in most of the cases, this is what is written in your textbook if you have studied, most of the time m will be equal to k. K can never exceed m. It cannot be more than m. In very rare cases, it is possible that k can be less than m. So that's why most of the time this should work for you. Without any bother that how I will calculate k, you can take it as equal to m. This is written in your textbook. In most of the cases, this is the situation. K, the reduction number can never be greater than m. In a very rare cases, it can be less than m. And I will give you example that why we need to consider k rather than m, because in very rare cases, I will give example in today's lecture. If we use m instead of k, we will not be able to solve the problem. So then in that case, we have to reduce m by, for example, 1 and try. So because, for example, here the three fundamental dimensions are present, and if you say that no, let m is equal to 2, then this is something saying incorrectly. Because we already say the three fundamental dimensions are present. So if you say that no, m is equal to 2, it means we are denying something which is already present. So to avoid this problem, we defined this reduction number k. Because if k is 3 or k is 2, so this is an appropriate way of doing or solving the problem. So I will explain later on. I finish these problem. I will give example that why we consider k rather than m and solve the problem. Clear? The idea in your textbook given is that why k is equal to 3, because they say that we consider these repeating variables. These are the repeating variables that we already consider. So these repeating variables, if you consider them rho vd, you can take them rho v by d, you can consider rho d by v, whatever combination you take, still you will get dimensions from here. Still you will get the dimensions. And this is actually the requirement for the repeating variable, that they should not form a dimensionless group among themselves. This is what we already discussed in the previous lecture. So the reason k is equal to 3 given in your textbook is like this, that because these three variables cannot form a dimensionless group or product among themselves, that's why based on this k is equal to 3. Once we calculate k is equal to 3, then step number 4 is to calculate the number of pi groups needed to solve the problem. And that is equal to n minus k. So 5 minus 3, 2. You see n minus m is also 2 pi groups are required. So you actually we mean the same thing. Clear? So now it means that we need 2 pi groups, 2 pi terms in order to solve this problem. And this is coming from the Buckingham pi theorem, which is very easy, which is stated here, very easy, but there is a proof available for this theorem, and that is not easy. So that you can find in some advanced fluid mechanics books. So 2 pi terms we need. Now the second question is, what are these two terms? This is the second question that we need to answer. So we go to step number 5. Because we have k is equal to 3, so you select 3 parameters as repeating variables. These 3 variables that we select, I already explained in the previous lecture in detail how you select them. These are guidelines available that can help you to identify the repeating variables. One of the reason was that these 3 should be selected such. In this case, it's not always that you have to select 3 repeating variables. No, that will depend on k. One of the thing is that they should not make a dimensionless group among themselves in any combination. Because if they make a dimensionless group, we have to combine it with one remaining parameter, then how the dimensions will be cancelled out? Because by definition, pi is dimensionless. Pi has no dimension. This is by definition. And the other guidelines that can help you to select these variables. And these are called repeating variables because you see they repeat in all the pi terms. Now, we identify that in order to solve this question, you need actually 2 pi's. We need pi 1 and we need pi 2 to solve this problem. So formation of this pi 1 and pi 2, there can be different ways to do it. There can be different ways to do it. One of the procedure to do it, that is by repeating variables. So we have limited time. That's why I will mainly focus on this repeating variable method of repeating variables. This is one way of forming these pi groups. There are other ways available also, but we have limited time, so we just stick to our textbook and follow this method of repeating variables. Because they repeat, and how we form the pi groups, and then we simplify, we assign these arbitrary exponents or powers. So how we make the pi groups? The 3 repeating variables and 1 non-repeating. The 3 repeating variable and 1 non-repeating. And for the repeating variable, we assign these arbitrary exponents. So you write down A1, B1, C1, A2, B2, C2, you write down X, Y, Z, whatever notation you use, it doesn't matter because you already know in the end we calculate their values. So you write down A, B, C, you write down X, Y, Z here, it doesn't matter because in the end we calculate their values. So now we have to simplify pi 1 and pi 2. So step number 6 is we go for pi 1. So what we do is that because by definition pi 1 has no dimensions, so that's why you can see that m power 0, l power 0, t power 0, it is 1, no dimension. This is pi we can write down in this fashion here. By definition, pi is dimensionless. And we put the dimensions for the parameters here, rho, d, v, and mu, with these exponents. So you put the dimensions, and as I said before that the methods of dimensional analysis that we discuss here, what is the basis? The basis is principle of dimensional homogeneity, which is written PDH in your textbook. PDH, principle of dimensional homogeneity. So what is principle of dimensional homogeneity? That the dimensions on the left hand side of the equation must be identical to the right hand side of the equation. Clear? So based on that, we can write down for m 0, then m is here exponent a1, so it is a1, and then here m, this is exponent 1. So that's why we write down 1 here. So this is how we can write down based on the satisfaction of dimensional homogeneity. You satisfy dimensional homogeneity, this is how we can write down this equation 1 for M. Similarly for T, L and T. So you can see here that we can write down these equation 1, 2 and 3. Now we have 3 equations. This is equation 1, equation 2 and equation 3. And we have 3 unknowns, A1, B1 and C1. So we can easily solve and we can calculate their values. And you put them back in this pi 1, their values here for the exponents that we develop. We calculate. So you simplify. So this is mu divided by rho dV. Now we already studied some of the dimensionless numbers. There are many, but a few we studied in this chapter. You can look for those familiar dimensionless numbers. For example, we already know that this rho dV by mu, this is actually a Reynolds number. This is Reynolds number. When you come up to this stage here, when you put the values for the exponents and you calculate pi 1, you must check that there should be no dimensions here. You must not get any dimensions, no dimensions, because by definition pi is dimensionless. So there should not be any dimensions here, no dimensions. This will be a check on your calculations. If you put the dimensions here and you get any dimension remaining, you make a mistake. Go back, see where is the mistake. Now in this case it is easy because I know that this is the Reynolds number. So Reynolds number is a pure number, no dimension. So it means that there is no possibility of mistake so far. So we come up to here in the previous lecture. Now we next continue for this pi 2, the same procedure, but now we go for the pi 2. So for the pi 2, we have this m power 0, l power 0, t power 0. Pi has no dimensions. And we put the dimension for the parameters on the right hand side of this equation with arbitrary powers, a2, b2, c2. You can write down x, y, z. Really doesn't matter because we calculate their values. So again we go for m, for l and for t. We make these expressions. How? We satisfy the dimensional homogeneity. Clear? So you calculate the values of these exponents and then you put them back here and you simplify. Now in this case, when you solve for this pi 2, is this correct or this is incorrect? How you know? So to check this, you can put dimensions here. Put the dimensions. So you see that f we can write down ml by t square. ml by t square. Then we have rho. So the dimension for the rho are m divided by l cube. Then we have d square. So d is l and then you have l square. And then you have v square. So it is l square divided by t square. So you can see here this t square cancel out t square, m cancel out m, this l square make this cancel and this one l will cancel the square and this l will cancel this l. So no dimensions. This will be a check on your calculations that you make any mistake here or not. If any dimension is remaining here, it means you have made a mistake. Go back and see where is the mistake. Why you should not get any dimensions here? Because by definition pi has no dimensions. So if we say left hand side is equal to the right hand side, then in that case the dimension must be identical on both sides. So this is how we now calculated pi 1 and pi 2. So now the step number 7 is that we can write down f1 into this pi 1 and then pi 2 equal to 0. Now in this case, you see that I can write down this pi 2, that is a function of pi 1 inverse. Now if you remember, we studied in step number 7, the last step of the Buckingham pi method, that we can arrange the pi groups as desired. Just like you see here. This is what I write down earlier in the previous lecture. You can see here, once we can write down these pi groups n minus k, this is required to solve any problem. So we can write down pi 1 as a function of pi 2, pi 3 and so on. You can write down pi 2 as a function of pi 1, pi 3 and so on. You can write down pi 3 as a function of pi 1, pi 2 and so on. Similarly, we can write down, let's say pi 1, you can take inverse of it. You can raise power of pi 1 by a square. This we do it, this is what we say manipulating. The reason behind this is that dimensional analysis does not provide complete solution. This is what we discussed in the previous lecture. That is the fundamental limitation. So that's why we can write down in this fashion just to get the desired result in the end. So that's why sometimes maybe we need to take inverse of a pi, square of a pi. And the reason is why we do it, that we want to find the desired form of the equation. And why we can do it, that you can take inverse of a pi or square of a pi or product of a pi. The reason is that this is justified. How it is justified? If you take inverse of a pi or you take square of a pi, still it is a dimensionless. It is not going to bring dimensions, so that it becomes incorrect. So this is what is written in your textbook, that if we do it, it is justified to get the required form, and on the other side it will still remain as a dimensionless. So remember, this dimensional analysis does not provide complete solution. It provides partial solution only, but still you can see that these expressions we already discussed before, and you apply the dimensional analysis, you get those expressions. We cannot say that this is incorrect. We already know that, you see from dimensional analysis, that this pi is actually equal to some coefficient, and that coefficient is a function of the Reynolds number. And that coefficient, if you remember in the previous course, we said that is the CD, the drag coefficient. And it is true. If you remember, we discussed the three-dimensional body drag forces on three-dimensional 3D bodies and 2D bodies. The graph that we draw, that was actually with the Reynolds number. So it is correct. It means that this dimensional analysis, that's why it is very powerful tool, even though it does not provide the exact functional relationship or 100% solution to the problem. If you remember, we studied a graph like this in the Fluid Mechanics 2 course. It was the Reynolds number, versus the CD. And I explained actually for 2D and for 3D. So it was a graph like this. Clear? So you see, this is what the dimension analysis is telling us. Now, the dimension analysis does not provide complete solution. This is written in your textbook, but still you see that it guides us to the right direction. That's why dimension analysis is very powerful tool. So this is the end of the problem. Now the next thing here is that we select this row VD as repeating variables. So you can ask a question that if I select, for example, mu as a repeating variable, then what will happen? So for example, if we select VD and mu as repeating variables, then these will be the pi groups. You see mu is now repeating, and this will be the pi2 group, mu, v and d. So you can select these as the repeating variables. When you solve the problem like we did here, you will get this as pi1 and this is pi2, which is again a Reynolds number. So one thing to understand and learn from here is that still we have pi1 and pi2. Still you have pi1 and pi2. For any question, for example, for this question, the number of parameters were 5. N was equal to 5. And M equal to K that we took in this problem, that was equal to 3, the number of fundamental dimension present. So N minus K or M, that was equal to 2. It means you need 2 groups to solve the problem. Because this is coming from the Buckingham pi theorem, this is fixed. In solving this problem, this pi number of pi groups, this will not change. You cannot say that if somebody else will solve this problem, he or she may have 3 pi's to solve the problem. This is not possible. You solve it 2 pi groups, somebody else solve it still 2 pi groups. Because this is coming from the Buckingham pi theorem, that cannot be different. So that is fixed. Regarding the formation of the pi groups, this is not fixed. For example, you see here, in the first case, this was the pi1. And now in this case, we change the repeating variable, this is the pi group. So these are not the same. So remember, this is written in fluid mechanics books. The number of pi groups, that will not change. That will remain the same for that specific problem. But the pi terms, that are not unique. For example, somebody solve in this way and get these as the pi groups. This is pi1 and pi2. Still, the solution is correct. Somebody take these as repeating variable and get this pi1 and pi2. Still, the question is correct. One thing to remember here is that, for example, we write down here phi. And here, because the pi groups are not exactly the same, you see this pi1 here is different than pi1 in the previous. So that's why we cannot say that phi is equal to g. This nature will not be then the same. This we cannot say. So this actually, we are looking to the same problem from 2 angles now. In one way you get this situation, in another way you get this situation. Both are correct. Both are correct. Maybe that you want to calculate the phi or you want to calculate g, because this will come from experiments. As we said before, that F1 and F2 must be determined experimentally. That is why we say that dimensional analysis does not provide complete solution. It cannot calculate the value of phi and g. These must be determined experimentally. So when you conduct experiments, for the first case, you will have a setup of experiments. For this case, you will not have exactly the same setup of experiments because you are exploring a different situation. However, if you want to calculate or extract the value of fd, then that must be the same in this case or in this case. That should not be different, that you have drag force values different and the problem remains the same. So these are a few things that you should remember when you apply these methods of dimensional analysis to solve, because tomorrow you will be a researcher and you will interact with fluid mechanics problems. So you have to take care of these basic understandings, which I said that these topics are conceptual, and if you do not understand, then there is a possibility that you can make a mistake. Clear? So let us continue with this now. I consider another problem, even though it is sufficient uh, for class point of view, but still I try to solve another problem as an exercise for you and better understanding. So this is again from your textbook. Derive an expression for small flow rates over a spillway in the form of a function including dimensionless quantities. Use dimensional analysis with the following parameters. We have height of the spillway, P, head on the spillway, the water, viscosity of the liquid, density of the liquid, surface tension, and acceleration due to gravity. So actually this is the situation which is given to us. We have this spillway over which the water flows and the different parameters that are given in the question. So you can see that in the previous, as I said, because we develop a functional relationship here, so in step number 1, if you miss any important parameter, definitely the result will be incomplete. And if you bring unimportant parameter, unnecessary, insignificant parameter, that will increase your calculation. Maybe then you need more than 2 pi terms, but of no benefit. So that's why these are very important, that you must have good understanding of the problem. But here the idea is to apply these methods to learn. That's why these parameters are given to us. Now we list the number of parameters. Actually, a similar question, that is a solved example in your textbook. And the number of parameters there are less than this. So that is actually a special case of this problem. I try to solve this complex problem so that that problem becomes easy one for you to understand. So this, you will also find a similar problem as solved example in your textbook. Now the first step is to identify and list the parameters. So this is how you will list the various parameters and you will calculate n. So the number of parameters are 7. So I will try to be a bit quick here. So the second thing is you select the MLT system and we define here the dimensions of the different parameters. You can see here, if you make any mistake here, definitely there will be a problem in solution. So you can see here that L is present, M is present, T present. So that's why M is equal to 3. All the 3 fundamental dimensions, they are present. So M is equal to 3. Now the Buckingham Pi method says that n minus m, that is the number of dimensionless groups are needed to solve the problem. The question is, these 7 parameters we can reduce to how many dimensionless groups? That is coming from the Buckingham Pi theorem. So n minus m. But as I said, maybe a situation where this will not work. So that's why we go for k rather than m. I will give example where it will be clear. So that's why step number 3 is to determine k is equal to 3. And the reason given in your textbook is that, for example, we select 3 these as repeating variables, they cannot form a dimensionless group. So this is the justification why k should be equal to 3. But you will see in most of the problem k is equal to m. So you don't need to actually worry about this too much. In very rare cases, it will be different, that I can give one example to illustrate, but k cannot be greater than m. So now step number 4 is that how many pi groups are needed to solve the problem. So n is equal to 7 and k is equal to 3. So we have 4. It means that we need 4 pi terms in order to solve this question. So because we have to select k number of repeating variables, that is why this method is called method of repeating variables. And we try to determine the pi terms. There are other ways of doing so, but we just stick to this one, our textbook, the method of repeating variables. So let's say these 3 are selected as repeating variables. You can try different and solve the problem, see what you get. That is your learning. So we select pi 1, and these are the repeating variables. You can see they are repeated in all the pi terms alongside with one non-repeating variable. So we assign these arbitrary exponents to the repeating variables a, b, c, or x, y, z. So we have to simplify now these pi terms. So for pi 1, we write down this here. Now you put the dimensions for the parameters that we already write down in step number 2. And we satisfy the principle of dimensional homogeneity. Based on that, we can write down this 1, 2, and 3 equations. That the dimensions on both sides must be identical. This is principle of dimensional homogeneity. So we can easily calculate the values of these because we have 3 equations, 3 unknown, we can solve. And then you plug in the values of these parameters back and you simplify, so you get the pi term. Now you see here P, what was the dimension of P? L. What was the dimension of H? L. So you can see here L divided by L, no dimension. It means that so far we have not made any mistake. If you get any dimension here, go back, where is the mistake? Because the definition, by definition, pi is dimensionless. So this is how you can check your calculations. Similarly, we go for the pi 2 and we repeat the process. Then principle of dimensional homogeneity, we go for M, L, and T. We have this equation 1, 2, and 3. And then we simplify, you get here. Now, is it correct? Put the dimensions. If you get any dimension incorrect. So this is now the form of the pi 2. Then we go for pi 3 and the same process is repeated. So this is how we get the dimensionless form. And also you need to identify the familiar dimensionless numbers. For example, this is Reynolds number. Similarly, we go for pi 4. We put the dimension and then we determine the values of these arbitrary exponents or powers. that we assign and we simplify here, again it turns out that this is equal to the negative square of the Weber number. Clear? This is how we can identify the dimensionless numbers that we are familiar with. So now we calculate the form of the pi groups. And step number 7 is that we can write down pi 2 minus 1 by 2 as a function of this. This we write down, the reason is to get the desired form. So as I said before, you take inverse of a pi term, you take square root, you take any power of the pi term. This is justified because it will still remain dimensionless. So based on this, we get this form here. That discharge over the spillway, this is, you see, square root of g h3 by 2. You see, we are getting familiar terms. That's what we studied before. We studied some introduction to the notches and weirs, broad crusted wear. So you see there what we studied here. A function of the, so we have the coefficient of discharge, clear, that we determine experimentally. You see, you study fluid mechanics 2 lab, so triangular notch, rectangular notch, for example, you determine coefficient of discharge experimentally. But at least from dimensional analysis, we know that function of the Reynolds number, the Weber number, if surface tension is significant, and to this ratio h by p. And this is actually what we studied. So although the dimensional analysis does not provide the exact form, but you can see that it guides us in the right direction. That's why dimension analysis is very powerful tool, and it is used in the research work, in the design of experiments. Clear? So this is how we use these methods. So just to conclude the discussion now, although we can discuss more and more about these things, but due to the time limitation, let us just conclude this dimension analysis. We studied that there are 2 methods of dimensional analysis that we study as part of this course. The first one is the Rayleigh method. So the Rayleigh method we already applied, but you saw that if the variables, they are more than 4, so then in that case it becomes very difficult to solve the problem. Clear? The dependent variables, especially if they are more in quantity, increases. For example, if we have 3 or 4, still we can solve. But if, for example, in any phenomena we have, for example, 7 variables, 10 variable, 20 variable, it becomes very difficult. You already saw this in the problem that we solved. So this is a very serviceable method, but it has been superseded. So that's why we are now studying the Buckingham Pi method, because Buckingham Pi method can be extended to any number of variables. That's why in modern fluid mechanics books that we write today, they mainly explain the Buckingham Pi method, because this method has been superseded by Buckingham Pi method. So we studied both in detail because both are given in your syllabus. So that's why we also studied Rayleigh method in detail. Now in this Buckingham Pi theorem, this states that there are n-dimensional variable in a dimensionally homogeneous equation described by m fundamental dimensions. They may be grouped in n minus m dimensionless groups. So in this case, what you studied is that instead of n minus m, we actually write down n minus k. N minus m will work most of the time. This will work. This will give us the number of pi groups needed to solve the problem. But in your book, instead of this, we go for n minus k. Clear? So let me give a quick example before we start the next chapter. You see here that find the reduction number k. So usually this equals m. It cannot exceed m, but rarely it is less than m. So most of the time this will work for you without bothering. Just calculate m and take k is equal to m. If not, then we reduce k by 1 and try to solve the problem. So that's why we determine n minus k, the number of dimensionless groups needed to solve the problem. So let me take an example before we start the next chapter. Very quick example to let you know that what can be the case where k may not be equal to m. So that will be rarely. Clear? You see, very rarely this can occur. Most of the time k is equal to m will work. For example, let me consider an example of a soap bubble. This is a soap bubble. Now we are interested to calculate the change in pressure, because you already know that there will be pressure difference between the inside and outside of this soap bubble. So let's say we have this as the radius r of the soap bubble. Clear? We are interested to calculate the difference in pressure inside and outside. So that is delta P. Now because this is pressure, so we can write down the dimensions here. We already now know that that will be equal to m into L minus 1 and T minus 2. What other parameter is present important? The radius. So we write down here the radius. So that will be equal to L. These are the dimensions. Now what else will be important? You see, if you do not know, you did not study such example before, you have to identify what are the important parameters. So if you miss important parameter here, you see the solution will be incomplete. Dimension analysis will not work if you miss important parameter here. Let us assume that because here the other parameter that can be important can be the surface tension that we denote by sigma. Clear? The surface tension. So what are the dimensions for the surface tension? This, in fact, in this problem we write down here the dimensions of the surface tension here, m by t square. So we have m by t square. So we can write down here m into t minus 2 or m by t square. Now you can see here that we need to calculate the number of variables in this problem. How many number of variables? 3. Next, you need to calculate the number of fundamental dimensions. So you can see here m is present, L is present, T is present. So that's why m is equal to 3. So now to develop a functional relationship for this case, how many pi's we need? So according to the Kingham-Pi theorem, number of pi's to solve this problem will be n minus m. So now you see that I will write down 3 minus 3 equal to 0. How you will solve this problem then? So in such cases, what we do, we define this reduction number k. Instead of m, because if you say m is equal to 2, you reduce m by 2. How can we deny this? Because all the three fundamental dimensions are present. And even they are not in fixed proportion. This is also written in your textbook. If these were present in fixed proportion, then we can reduce them by 1. By fixed proportion, I mean that let's say m by t square. And you also have m by t square, clear, in this case. So it means that then we must reduce this m. You see m by t square and m by t square, you see they are present in fixed proportion. This is written in your textbook. You read it. I try to explain it here by example. And it is written usually m and t in the problem. So you can see here m by t square, fixed proportion. So that's why taking m is equal to 3 will not work for you. So because this will not work for us, that's why as per our textbook, we reduce k by 1. So we take k is equal to 2 and then try to solve the problem. So in this case, number of pi required to solve this problem, that will be n minus k, and this will be equal to 3 minus 2 equal to 1. When this is the situation, so it's not that just reduce it by 1. This may also not always be the case. When you get this type of situation that we are unable to solve the problem, you should go back and identify if you are missing any variable or not. This should be the thing that we should do. You go back to step number 1 and see if you have missed any important variable, or you included unnecessarily parameters. This should be the first step. If you are sure that this is correct, and this is correct, then what you do is that reduce k by 1 and try to solve the problem. So this in very rare cases, then in this case you see that m is not equal to k. In most of the cases, m will be equal to k, and k can never be greater than m. This will never happen. So mostly it will equal to k, and sometimes in very rare cases like this example may not be equal to k. These steps are from your textbook. So usually this equals m, which it cannot exceed, but rarely it is less than m. So I explain it by an example. So we can continue with this discussion on similitude and dimension analysis. We can go more into the depth and solve the problems, but we have limited time. So that's why I stop it here. In fact, I try to cover more than what is given in your textbook. So the next important chapter that we need to start is Introduction to Sediment Transport. Now, this is actually a full course, as I explained said before, but we will try to cover some basics related to the sediment transport. So first I will try to highlight the importance that why we need to study this topic, and then we will try to cover some basic topics within the allowable time in this lecture and in the next lecture. So let us start with some basics. So waters flowing in natural streams and rivers have the ability to scour channel beds, to carry particles heavier than water, and to deposit materials, hence changing the bed topography. This phenomena, which that is sediment transport, is of great economical importance. So what we see actually, these sediment transport processes that we are going to study, these are naturally occurring. These are not new topics that we learn today. These are happening since the natural processes are started to occur on the surface of the earth. So you can see here water is flowing in natural streams and rivers. This is happening since the beginning. Have the ability to scour the channel bed. This is happening. Water carries particles along in the rivers and stream. This is happening. And then those particles, when the water stops somewhere, so then those materials settle down. So that material is deposited, and because of that, what happening is that the bed topography of the streams and rivers, they are changing. You already know that the rivers, they change the course over a period of time due to these different conditions. So this thing is happening. Now why we are interested in this sediment transport? This is of great economical importance. For example, to predict the risks of scouring of bridges, weirs, and channel banks. So you see that in the channel, the water is flowing in this river and stream. So it has these banks which contain the water and the water flows. If we change the course of this channel, for example, we have sediments coming in the water, they are deposited here. So what will happen? That they will reduce the discharge carrying capacity. And ultimately, it will result into overflow of these banks. And this is what happens in floods. It can overflow. And when it overflows, what will happen? There will be communities living on both sides of the river, and those areas will be flooded. So you see that there will be loss of property and loss of lives. Similarly, for example, we have a river, and this river is built on, let's say this is natural river, and we have a reservoir that is built. So what is happening is that it stores the water, and when this water here it is coming, sorry, this water will remain for some time in here. The velocity will reduce before it is allowed to pass over the dam or through the tunnels, and it continues to flow downstream. So as a result of here in the reservoir, what will happen? These sediments that will settle at the bottom. And when these settle down, what will happen? Let's say they settle up to here. They will reduce the storage capacity of the reservoir. For example, scouring of bridges, you already know that, let's say we have this river cross section, and on this we have bridges which construct a bridge. Let's say this is a bridge, and in the bed of the channel we have the bridge piers. So you see, as the water moves, there may be scouring here, removal of material here. I already give you some examples in the introduction of this course. Water can remove the material from here. So it can pose threat to the foundation of this structure. So if this bridge collapses, you can see here that it will be of great economical importance. To predict the risk of scouring of bridges, weirs, and channel banks. to estimate the siltation of reservoir upstream of the dam. This is what I already explained. As these sediments are coming, they get deposited, then next time up to here, then up to here, and up to here. So you can see the storage capacity of the reservoir is affected. In fact, the life of the reservoir will depend on this sediment inflow to the reservoir. And these sediments are coming in water. For example, the water coming to the Tarbela Dam from the natural river, that is the Indus River, that is originated in the northern areas. And they bring along these sediments due to the processes of weathering and erosion that you studied in geology. And those sediments are carried and ultimately they are deposited here. So based on this, we say that the life of reservoir is affected by these sediment inflow to the reservoir. So we want to estimate the siltation in the reservoir so that we say that, for example, what is the life of the Tarbela Dam? How much we can continue to operate next 20 years, 30 years, 40 years, how we say this? This we determine, we estimate the siltation, that how much it will be completely filled with the silts and no longer it can serve the purpose. To predict the possible bed form changes of rivers and estuaries. This I already explained here, that because of these sediments, what will happen if they are deposited, the discharge carrying capacity that will be affected. Actually, we want to predict the possible bed form changes. You might have studied or seen that the river, it changes its course over a period of time. So actually we are interested to predict the possible bed form changes. This is geomorphology of the rivers. And estuaries, I will show you some picture also. Estuaries, they are the coastal areas where the river joins the ocean and the sea. So you can see here that we are very much concerned with these problems. So these are basically coming from as a result of this sediment transport in rivers and streams. Numerous failures, they resulted from the inability of engineers to predict sediment motion. What happened is that failures occurred. I will show you some pictures that resulted because of inability of engineers. You did a study, for example, in your degree courses, and then you go and design that dam, for example. So you have inability to consider that problem, and that resulted into numerous failures. Or you do not have sufficient knowledge in that area to predict the sediment motion, and as a result failures resulted. For example, bridges collapsed, formation of sand bars in estuaries and navigable rivers. As I said, that you have this river, and when the water is very shallow, you will see, especially the sand bed river, these small islands will form when the water is very shallow. So the water will flow like this. It can go like this, this can go like this, no problem. But these small islands which you can see form, I will also show you some pictures. These are sand bars. Destruction of banks and levees, which I already explained. So you can see here that these all resulted, these failures, because in the design of these structures, engineers had not sufficient knowledge to predict the sediment motion. You can see here the transport of sediment is often more visible in mountain streams, torrents, and creeks. Torrents, what we call tufan. So in mountain streams, torrents, and creeks, sediment transport is more visible. You can see here, for example, this is a picture. So you see the water will flow, and you see how much these sediments, these are carried from different areas and then deposited along the river. Whenever the velocity is reduced, the sediments will get a chance to settle down, depending on the transporting power of the medium, the water in these rivers. So these are commonly visible in mountain streams, torrents, and creeks. Creeks are narrow passages. However, large rivers are also famous for their capacity to carry sediment load. For example, the Nile River that is originated in the Ethiopia, passing through Sudan and then into the Egypt. Nile River, Darya Nile. So the Mississippi River in the US and the Yellow River in China. So the Nile River, which is about 6,700 kilometers long with mean inflow is about 3,100 cubic meter per second. Large floods take place each year from July to October with maximum flow rates of this much, during which the river carries large sediment load. The Mississippi River is about 3,800 kilometers long. Its mean annual discharge is 17,000 cubic meter per second. On average, the river transports about 7,000 kilogram per second of sediment in the Gulf of Mexico. You can see the implications of carrying this much sediment in water. The Yellow River in China flows 5,460 kilometers across China. The annual mean flow is 1,530 cubic meter per second, and the average annual sediment load is 1.6 billion tons, which comes primarily from the middle reach regions. You can see the color of the Yellow River. This is because of the sediments it carries. On average, 1.6 billion tons, average annual, clear, per year. So what could be the implications of, you see that these rivers, they carry these sediments. Let us take a break, then we will continue after the break.